Welcome back. We are working on heat matters, note 4B today, talking about phase change. If you have not yet done notes 4A, which would be in Tuesday's folder, please do that because you won't be able to do the quick review, and these kind of build on that. So go back to 4A first if you haven't done that already. But here we go with 4B. I want you to pause right now and fill in the quick review up here at the top. Use the word bank down here. And when you're all ready, unpause and I'll be giving you the answers. Welcome back. Here we go. All right. So heat and temperature are not the same thing. Heat is the transfer of thermal energy from one object to another. Temperature is the measure of particle motion. There are three main temperature scales, and those are Fahrenheit, Celsius, and Kelvin. The boiling point of water is 100 Celsius to 12 Fahrenheit. Freezing is 0 Celsius and 32 Fahrenheit. The Kelvin scale is special because on this scale, 0 degrees is the point of zero particle motion, which is called absolute zero. And this was all stuff that we talked about in notes 4A. So make sure you've got that written down, and then we'll move on. All right, so this graph is a basic copied a million times phase change graph. So if you look up phase change diagram or phase change graph on Google, you'll find this and a million other similar sorts of things. It's presented in a number of different ways, but it basically ends up looking the same. Since this particular one has no specific temperatures or times, this could be a phase change graph for almost anything. And I say almost because there are some substances that don't move through all of the phases of matter. There are some substances that go straight from a solid to a gas, like carbon dioxide. And so you wouldn't have this liquid stage because it doesn't have it. It would skip over it. But for most anything else, the temperature would change depending on the boiling point and the freezing point of that matter, but how it does is the same. So let's look at how it does. So what exactly is happening here? All right, so mentally, I want you to take an ice cube out of the freezer, put it in a cup, and set it on the counter, right? You've done that? All right, what's going to start happening to our ice cube? Right, it's going to start melting because the air in the room is way warmer, like 73 degrees most likely around in there, than the ice cube, which is going to be 32 or lower, or 0 and 22 if we're talking about Celsius. So the warm air is going to be, it's going to heat, it's going to be transferred into that ice cube, and it's going to make those particles move faster. And so the heat energy is going to go up, and the temperature is going to go up. And as it rises and rises and rises, eventually it'll hit this spot right here, which is the melting point. If we're talking about water, because we're talking about our ice cube, that's going to be our 0 or 32, depending on whether you're talking Celsius or Fahrenheit. Now, some of the particles in that ice cube have turned into liquid, but at this point, there is still some solid particles in our sample as well. What's crazy about phase change is, you see how our line flattens out? Now, what do we know about graphs? What do we know? If the line just does this from our X and Y axis, we know it's got a steady rise and run, right? But that's not what's happening here. So we can tell that the temperature is not changing. The temperature is staying the same, but the heat energy is rising. The heat energy is still going up, but what is that heat energy being used to do? It's not being used to raise the temperature. It's being used to excite the particles so that those ones that are still solid will break apart into a liquid. And then once every single bit of that ice cube is now liquid water, It's still 32 degrees, but now it's all liquid water. We have this increased heat energy that has it being all liquid water at 32 degrees instead of ice at 32 degrees. Do you see how those both can exist because of the amount of heat energy, how fast the particles are moving? Okay, so it's on the counter, right? So it's got to get 32. We're still going to keep going. So the heat is going to keep on rising, and it's going to get to room temperature, about 22, 23 degrees Celsius, about 72 degrees Fahrenheit. And at that point, we're going to put it on the stove or put it in the microwave or something. We're going to do something where we add more heat to it than the room could add. The temperature is going to rise, and the heat energy is going to rise. And that liquid is going to get all the way until it gets to this point right here, which is 100 or 212. And at that point, the water begins to boil. The individual particles begin to get so excited that they jump out and away from the liquid water sample. But again, you can see the same thing happens where the heat energy is increasing the whole way. But at some point, we get to this point right here and the temperature stops. And that heat energy is being used to excite the particles and get them all to be gas instead of some liquid and some gas all existing at the same temperature. So once that heat energy is applied and we get all the way to here and our entire sample is in a gas, the heat can now then be added to it. And that's why steam burns are so bad, because steam can get hotter than 212 degrees. And that's why steam has so much energy as well. All right, so let's put a lid on it. All right, so we've got it boiling. The water's trying to boil away. It's turned all in. We got a pot full of steam at this point. We're going to put the lid on it. Turn the heat off. As soon as we put the lid on it, some of the water, some of the steam is going to hit that cold lid and condense into liquid water. So boom, we've already got some liquid water. But the temperature is going to come steadily down. And oh, I forgot to tell you this. Hopefully you haven't been trying to write this all down this whole time. This is just to listen to, because writing this down on yours would be difficult. My bad. Anyway, so we put our lid on and it starts to cool down. We take it off of the heat. It starts to cool down. It gets to this temperature, which is 212 or 100. And the particles then, as the heat energy is being removed, slow down, but they stay at 100 and 212 until every single particle has slowed down and become liquid water. And now we have our liquid water that cools down to room temperature. All right, we got to take our room temperature water and stick it in the freezer. So again, heat energy, the heat energy is coming down, the temperature's coming down. We get to this point right here, which is 0 or 32, freezing point, and that's when the liquid particles start to lock into a solid. The heat energy is still being removed, but the temperature stays the same until every single particle has locked into a solid. And then once it's there, the temperature can then continue to drop. All right, so I've just explained it to you in a very wordy way. I want you to take a minute or two, pause the video, and fill in these 2 lines in your words. What did I just explain? All right, welcome back. So now I'm going to give you my notes of what I just explained. So this infographic shows that as heat energy increases, temperature also increases. In addition, we can see that once a phase, and that's just a fancy way to say state of matter, so a phase or a phase change or a state of matter change occurs, the temperature remains the same as the molecular actions of melting, boiling, condensation, or freezing happens, and continues to stay the same until all of the particles in the sample have gone through that action. Whew. All right, pause it if you need to. I'm cleared it and moving on. All right, so now it's your turn. I want you to fill in the phase change diagram. So rewind the video a bit, go back, look at what we just did and see if you can figure it out. I will give you a hint that the arrows are the actions. So the arrow is for the molecular actions and the dotted lines are for the phases or the states of matter. So you've got a word bank up here. And I'm telling you that if it's an arrow, you're going to write an action over top of it. So these you're going to write actions over top of. And if it's a dotted line, you're going to write the phase or state of matter. All right, pause it and do that. All right, welcome back. Here we go. Of course, we've got solid, liquid, and gas. All right, so now, as we are going from a solid to a liquid, that action is melting. As we're going from a liquid to a solid, that's freezing. As we go from a liquid to a gas, that's boiling or evaporation. And as we go from a gas to a liquid, that's condensation. All right, pause that if you need to. I'm moving on. Here's another way to look at the same thing. So again, I want you to take a minute, pause, and see if you can figure it out, and then come back and check your answer. Okay, so A is just the baseline. It's just the starting temperature of the object. That's the temperature of the thing when it's a solid. All right, so as we move up, we get to point B, which if we know that this is a solid, this is a liquid, and this is a gas, and we know the actions that are going to be happening on either side from up there, that means that point is the whatting point. What action is getting ready to happen as you hit that point? Right, melting. So that's the melting point. So then point B is the same temperature, but it's a different amount of heat energy. So what is point C? It is, right, freezing point. So they're both 32 degrees, but they have different amounts of heat energy. There's a different amount of heat energy and time that's passed. All right, so now we're going from a liquid to a gas. As we're going from a liquid to a gas, point D is the first point we hit, and that's the point at which it, right, so that's boiling or evaporation point. And then finally, point E is the same temperature, but it's the point that you hit as you're coming down from a gas to a liquid. So that would be condensation point. All right, pause it if you need to. I'm moving on. All right, so looking at our phase change diagrams, what do we know about what happens when heat is added or removed as far as particle motion is concerned? If I've got particles moving around and I add more heat energy, what's going to happen? Right, they're going to move faster. What if I remove heat energy? They're going to move slower. So temperature goes up, particle motion goes up. Temperature goes down, particle motion goes down. All right? And you can write up and down instead of the arrows if you're typing this at home and don't know how to do an arrow. All right, so last, we've got these little statements, and I want you to decide first, is it adding heat energy or is it subtracting heat energy? So we're going to put a little X if it's adding, we're going to put a little O if it's subtracting. So ice cream melting. It's going from a solid to a liquid. So that's going to be, right, adding. A puddle evaporating. So it's going from a liquid to a gas. Right, adding again. Okay, pause and do the other three. Okay, so water droplets freeze into snow. We're going from liquid to solid, so that's subtracting. Dew forming on grass is water condensing from a gas in the air into a liquid on the leaves, so that's subtracting. And dry ice sublimating into CO2 gas is when dry ice is a solid and it goes straight to a gas. There's no liquid form. But if we're going from a solid to a gas, that means we are adding heat energy. So now we got to describe the particle motion. So let's go ahead and describe the particle motion for each of these with like a word or two so we can make it easier. So we're going to call solid packed, we're going to call liquid flow, and we're going to call gas fly. That's what happens with the particles. In solid, they're packed. In liquid, they flow. In gas, they fly. All right? So if we're going ice cream melting, We're going from a solid, the ice cream, to a liquid. So solid to liquid, packed to flow. You get it? All right, go do the rest of them. Pause it, and then do the rest of them, and then come back. All right, here we go. Puddle evaporating is liquid to gas. So that's going to be flow to fly. Water droplets freezing into snow is liquid to solid. So that's going to be flow to packed. Dew forming on the grass is gas to liquid. So that's going to be fly to flow. And dry ice sublimating into gas is solid to gas. So packed to fly. Packed to fly. Let's go on a vacation. Anyway, that's it for these notes. Have a lovely day. Make good decisions. Bye.